Hi guys, my name is Ernest and this is Ernest Sciences and Mathematics TV channel. I'd like to welcome all members to my discussion for today, and I'd kind of like to request us to subscribe and get us in the comment section and also ring that notification bell to be getting various updates that we do in mathematics and sciences. Now in our discussion today, I'm going to look at one of the concepts in electricity and magnetism, and this basically is going to cement on the previous videos that we have done heavily on the concept of electricity. Now, in this specific case, we are going to look at how materials are going to be allowing this aspect of a current to flow through them. And of course, in this case, we are going to look at an aspect of three sets of materials for the specific graphs which I have given on my right side of the board. Now, in our previous discussion, we had discussed on the concept of conductivity, and we said that basically we are going to look at this specific aspect of conductivity in terms of materials allowing the flow of current. And of course, this gave us some of the, characteristics which we had listed and said basically that materials, this aspect of materials is going to be specific on, conductivity is going to be specific on some of the materials. And in that case, we had considered the concept of metals, semi-metals, and perhaps some of the aspects which we are referred to as superconductors. Now, we're going to look at these specific graphs in terms of the comparison between conductivity and temperature, and that is going to give us a clue in some way how we can relate this aspect of conductivity and temperature. Later on, we are going to see the relationship between conductivity and resistivity, and that's going to form our final bit of this specific discussion. Now, we had basically mentioned that resistivity can be defined in this way as the ability of a material or resistivity of a material is the ratio of the electrical field in the material to the current density. And in this case, we had, of course, looked at this one in terms of a ratio. And therefore, we can define resistivity as the ratio of this specific electrical field in the material to the current density. And this can be given in terms of rho. So I'm going to have rho given in terms of the ratio between the electric field in the material and to the current density, which I'm going to give in terms of this specific notation. And therefore, this is going to form a specific definition in terms of perhaps this particular equation of aspect of what we refer to as conductivity. Now, in this, or resistivity of a material. Now, in this case, we're going to also look at the concept of conductivity. Now, that, as I had mentioned, basically, the two are going to have a specific relationship, whereby we're going to see that conductivity basically is going to be the reciprocal of resistivity. Now, therefore, we are going to have this one perhaps given in terms of, let me use this one. I'm going to use another symbol for that one. Perhaps I can use a sigma to represent this aspect of conductivity. And therefore, we're going to have this sigma represented as the reciprocal of conductivity given as such. So in summary form, we are going to see that this basically is going to be the relationship between the two, and therefore this is going to assist us in trying to compare the aspect of either of the two in relation to this aspect of temperature which I've mentioned. Now, in this particular case, then therefore we're going to look at, I mentioned that we're going to use some specific aspect of the SI units, whereby we have said that we can give this sigma, which is conductivity in terms of the SI units, and these are going to be particularly given in terms of this specific symbol, which I've mentioned as the reciprocal of rho, and therefore the SI unit for this one is given. Perhaps write them in this specific, just a summary form. These are given as per ohm per meter, are given as such. So these are going to be the SI units which we are going to use in trying to represent this aspect of conductivity. And in actual sense, we are also going to use this aspect of resistivity, whereby we are going to say that conductivity basically is the reciprocal of resistivity. And in our description for that one, perhaps I can use this one given in terms of per ohm. In this case, we are going to come across some of the text which have been indicated as such, and of course, are given in terms of Siemens. So I'm going to elaborate on this one as we go by in our various discussion on this specific concept of the two, especially when we're going to come across our discussion on the particular problem sets which we are going to come across. But not to greater emphasis on that one, I'm going to look at some of the effects of this aspect of temperature, which I've mentioned on the two specific aspect of conductivity and resistivity. And now particularly I'm going to emphasize on the concept of this specific aspect of conductivity, which I've given on my right side of the board rather. Now conductivity is going to decrease with temperature, it's going to increase with temperature, but resistivity is going to, we're going to see that conductivity basically is going to decrease. So we're going to have this aspect of conductivity decreasing with temperature. So I can give this one in this specific form, but we're going to have a resistivity increase with increase in temperature. And this basically are going to be more elaborate when we are going to look at the structure of various conductors which we are going to consider. Now in this case, I just mentioned this one. So I'm going to consider this specific illustration for the graph that I've given for A, B, and C implying metals. So these ones are going to be a graphical representation of this specific aspect of resistivity against the temperature. And then we're going to consider resistivity against temperature for materials which we are going to refer to as semiconductors. And then we shall look at materials which are referred to as superconductors. Now, in this particular case, we're going to see that the influence of temperature is going to have a specific effect on these materials of metals, semiconductors, and the superconductors in that particular case, whereby we're going to see that some of the relationships are basically going to be behaving in this specific case, whereby we're going to have an increase, of course, in resistivity with increase in temperature given as such. So in this case, if we try to have this lower line, which I've particularly given at that specific point, we can find the slope at that particular point, which is going to be given in terms of the slope is equivalent to rho naught, and then we're going to have alpha. Now I'm particularly going to define this specific concept of alpha as we go by, but this is going to be the graphical representation of the behavior of resistivity for metals against the temperature. Now if you consider for the semiconductors, we're going to see that resistivity is going to decrease with an increase in temperature. So this specific graph is going to be having an increase in temperature towards that specific section. So if you try to see at the temperature at this specific point, if it is T1 for resistivity, perhaps this is going to be rho naught, it's going to be low. But as we go by, we're going to see that at the temperature T2, which is greater than T1, of course, the resistivity will have decreased to rho 1 given as such. So therefore, for the semiconductors, resistivity is going to decrease with the temperatures shown from the graph above. And generally for the last one, which is made up of semiconductors, superconductors, or rather in that specific case, now we're going to see that these are materials which are going to exhibit a high level of resistivity as the temperatures go by that specific point. Now the temperatures below T, I'm going to give this one as T subscript C, and this is going to be at the temperature to which below this point the resistivity is going to be 0, which means they are going to be conducting at an abnormal degree, as we are going to see in this particular case. So basically this is going to form a summary of what we are going to be emphasizing on the concept of conductivity, and they are going to assist us in trying to define some of the characteristics which we might come across insofar as conductivity is concerned. Now in that particular case, we're going to also see that basically we can explain this particular behavior, especially in relation to temperature for conductivity and resistivity, whereby we are going to see that an increase in temperature is going to mean that we are going to have, suppose we have a conductor of this specific nature. This conductor is going to consist of ions which are going to be either positively or negatively charged in the structure of this particular substance. or perhaps a conductor. And then we're going to have other molecules or other particles which are going to be indicated as such. Of course, we are going to be having other materials like that. Now, these ones are going to be charge carriers so long as they are going to be charged. And therefore, as the charges are going to move across these specific conductors, they're going to have a collision with either ions, atoms, and other molecules which are going to be found within this structure of these particular materials. Now, an increase in temperature is going to be disturbing this specific lattice or the structure of this particular material, and therefore that's going to, of course, disrupt the flow of ions, which basically constitute the flow of current, which we had mentioned from our previous discussion. Now, in this case, therefore, an increase in temperature is going to increase the level of disturbance, and therefore that's going to hinder the flow of ions and therefore increase in resistivity of this specific material. And this is going to be due to the frequency of collisions of materials as the temperature increase, and therefore that one can explain this specific aspect of increase in the resistivity with the increase in temperature. Now we're going to see that in some materials we can have a linear relationship for resistivity of some of the materials that we're going to come across. And in that particular case, we are going to have some of the graphical representations having this aspect of resistivity being given using this particular equation. So at a particular temperature, we can give this one a specific representation for resistivity, which is given as rho t is equivalent to rho naught, and then 1 plus alpha t given as such. Now, in this case, we are going to have this one as the resistivity at temperature T degrees. And then for this one, this is going to be resistivity at a temperature when the temperature is equivalent to 0 degrees centigrade. So basically, the T is going to be equivalent to 0. And in this case, I've given a new notation, which I've given in terms of alpha. And this alpha is going to stand for what, or implies what we refer to as linear coefficient of resistivity. Now, this linear coefficient of resistivity can be given in terms of a ratio, whereby we're going to have this one given as rho t minus rho naught divided by rho naught times T given as such. So this T is going to represent our temperature, and therefore this is going to be the ratio between the difference between this one and the product of the two, and therefore it's going to represent linear coefficient of resistivity. Now, for some materials, as we're going to see, they are going to exhibit various, of course, forms of this particular aspect of resistivity. And in this case, I mentioned the concept of superconductors, semiconductors, and metals. And as well, we can check for insulators in some of our discussions. And of course, we're going to see that for insulators, for some insulators, semiconductors, our resistivity is going to increase exponentially with the decrease in temperature. And in that particular case, apart from this, we are going to come across some of the graphical representations, which are going to have this arrow T represented in terms of exponential curves. And therefore, we are going to have this one represented as where T is the temperature. And then we're going to have this one represented as E at the exponent of EGKT. And in this particular case, we have come across this specific denominator in our various discussions. That's a combination of Boltzmann's constant and the absolute temperature. And in this case, for the EG, this refers to what we call the forbidden gap energy. So it's going to be forbidden gap energy. And we have come across this specific term in some of our discussion. Of course, I'm not going to go into details about it, but we can check on what this basically implies. Now, I'm going to put a link of other videos which have similar discussions, and they're going to assist us in trying to interpret this specific aspect of a forbidden gap energy, which I've mentioned. And in this particular case, therefore, we take note of these particular representations in the concept of resistivity. Now, as we had said, of course, this is going to have a reciprocal relationship with conductivity, and therefore that's going to create an essence of the relationship between the two as I've mentioned. Now, catch us in our next video as we're going to look at a deeper aspect of this specific aspect of perhaps resistance, and this is going to form our final bit of our discussion, especially on the concept of some of the, of course, components which we had identified, especially capacitors, resistors, and other, of course, components which we're going to mention later. So that is it for now, guys. Bye, God bless you. Catch us in our next video.